Okay, make sure you're looking at Gertrude's diet, this problem. I'm going to walk you through this one more time because I don't think we ever quite finished. And then we're going to pause the video and give you some time to work on Susie's, whatever that says, Susie's age. Alright, but first let me walk you through this again. So Gertrude's diet, and the idea is Gertrude is probably feeling like she's a little bit overweight, so she's going on a diet, watching what she eats, eating healthier foods, hoping that her weight will go down. So as we look at this equation, yesterday we talked about what this part of the equation tells us. Okay? Remember, x is the number of weeks that have gone by. So every week is going to multiply by this number. So for example, if 1 week goes by, then we've got a negative 0.8. Okay, so that means we're going down 0.8. If 2 weeks go by, that's another negative 0.8, and so on, starting from some value and then going down 0.8, down 0.8, down 0.8. And this would be her weight going down every week. So what does the negative 0.8 tell us about this situation? It tells us that Gertrude is losing 0.8 pounds every week. The negative part of it is because she's losing that much weight. Okay? So you would write down something like this. She is losing 0.8 pounds each week. Okay, that's what the negative 0.8 tells us in this case. Now, who remembers what the 185 tells us about the situation? I know I'm not there, but I still want you to blurt out the answers, okay? Participate. What does the 185 tell us about the situation? Okay, hopefully somebody in the room said that's going to tell us her beginning weight, okay? This 185. This is the weight she starts out at, okay? Think about it. At the very beginning, we are at week 0. Week 0. And if we're at week 0, 0 times anything is just 0. So if we're at week 0, that 0 is really going to wipe out this entire term like this. Blam, it's gone. Okay, so that whole term is gone. So at week 0, all we really have is 185. That helps us know that right at the beginning, at week 0, she must have weighed 185 pounds to start off with. Okay? So what does the 185 tell us about the situation? Her beginning weight is 185 pounds. Okay? Alright, let me get that back out of there. Okay, so the number in the front tells us how many pounds she's losing every week, and this number at the end tells us her starting weight. Alright, this is going to be very similar to other problems, so really pay attention to that. Now, on the other hand, Larry started a diet on the same day as Gertrude. So this is the equation for Larry's weight, okay? Still after X weeks, same thing. So we're supposed to compare and contrast Gertrude's weight and Larry's weight, and we have to justify our answer mathematically. Well, there are two things that we can say. Comparing these equations, we should be able to decide who weighed more to begin with, And we should be able to decide who is losing weight faster. So let's start with the first question. Who weighed more to begin with? Okay, look at Larry's equation. Ask yourself how much Larry weighs at the beginning. And then look back at Gertrude's equation. Remember how much she weighs at the beginning. Okay, so remember, to begin with, Gertrude weighs 185 pounds. On the other hand, to begin with, Larry starts off weighing 243 pounds. So obviously, who weighs more right at the beginning? Okay, so that's the first thing that we're going to say. Larry weighs more at the beginning. Okay, now before I end that sentence, let's talk about the second question. Who loses weight faster? Well, remember which part of the equation tells us how fast things are happening. I feel like I should change colors right now. Remember, this is the part of the equation that tells us how fast Gertrude is losing weight. She's losing 0.8 pounds a week. That's a little bit less than a whole pound. Now, is Larry losing weight faster or slower than Gertrude? All right, I'm really hoping you said that Larry is losing weight faster than Gertrude because he's losing 1.8 pounds every week. That's almost 2 pounds. So he's losing weight almost twice as fast as Gertrude. Okay, so as we are comparing and contrasting, let's mention that Larry is losing weight much faster than Gertrude. So Larry weighs more at the beginning, but Larry is losing weight much faster than Gertrude. Okay? After how many weeks will Gertrude and Larry's weights be the same? I think the easiest way to figure this out would be to look at a table of values. In fact, eventually we will need 2 tables of values. Let's have one table of values representing Gertrude's weight over time, and then we'll have a separate table of values representing Larry's weight over time. If we compare those tables side by side, we can see at what point the weights are the same. So one thing that you might do is this is the type of thing in the future you might consider doing with a partner. If it's not a test, then one person could do Gertrude's weight over time, make a table on the calculator, and the other person in the team could do Larry's. And then you can have your calculator side by side and kind of compare. I'm just one man, but I will do the best that I can. So let's start with Gertrude's weight over time. Always reset your calculator at the beginning of the lesson. Remember, you can reset your calculator by hitting clear and on at the same time. I've already reset my calculator. Remember that if I want a table of values, I'll hit the table button. Here's where I will type in the equation that I want to make a table of. I'm going to start with this, negative 0.8x plus 185. negative 0.8x plus 185. Notice when you do a negative sign that's in the very front like this, you use this white negative button at the bottom. You do not use the subtraction key. The subtraction key is only for when it's in between terms like this. In the front, it's the white minus. So here's the equation for Gertrude. So I'm going to hit enter. For now, I'll let the table start at 0. Of course, it should start at 185. But let's go ahead and let it count by tens for now, so we can see what happens quickly. Okay, so now I'm looking at a chart of Gertrude's weight. Okay, so I'm seeing what's happening over time. At 50 weeks, she weighs 145. 60 weeks, she weighs 137, and so on. Her weight goes down from there. Alright, so here's a little snapshot, a small picture of Gertrude's weight over time. Okay, take a good look at that. So that's a small part of what was scrolling on the calculator. So I'm going to take another snapshot of Larry's weight over time. If I need to go grab more values, more pictures, I will. But obviously, if this were a test, what you could do is just record a table and write down a long list on paper for both people, and then you could compare side by side that way. But I've got a computer, so I'm going to cut and paste. So now it's time to take another look at Larry's weight over time. Again, that's negative 1.8x plus 243. So that's negative 1.8x plus 243. So here I'm going to look at Larry's weight. This is set to start at 50. I can adjust if I need to. I'm going to keep letting it jump by 10 for right now. Okay, so here's a snapshot of Larry's weight over time, and I think I'll cut and paste this so I can put them side by side. Okay, so on the left, here's a small picture of Gertrude's weight over time, and on the right, here's a small picture of Larry's weight over time. Remember, Larry started out weighing more. Larry weighed 243 pounds at first, and Gertrude weighed only 185. So Larry weighed more at first, but Larry is losing weight faster. So it's possible that at some point Larry will go from weighing more to weighing less because he's losing weight faster. And maybe we have captured that because, okay, if you look at after 50 weeks have gone by, who weighs more at 50 weeks? Okay, because here's 50 weeks, right, on this top line. Who weighs more at 50 weeks? Well, let's see, at 50 weeks, Larry weighs 153, and Gertrude weighs only 145. So Larry weighs more at 50 weeks. But 10 weeks later, at 60 weeks, who weighs more at 60 weeks? Well, at 60 weeks, Gertrude weighs 137, and Larry only weighs 135. So at 60 weeks, by the time we get to 60 weeks, Gertrude weighs more. So somewhere in between 50 weeks and 60 weeks, it went from Larry weighing more to Gertrude weighing more. Because we were counting by tens, we can't see the exact week where that happened. So what we would want to do is go back and not count by tens, but maybe start at 50 and start counting by ones, because somewhere between 50 and 60 it happens. So probably somewhere pretty close to 60, because look, 137, 135, those are very close together. So let's go back and take a look. So here we are back at the calculator. I still have Larry's information in here. But if I just hit the table button again, so I'm still looking at Larry's equation with his 243 start weight. Let's see if I hit enter right now. So I'm still going to let it start at 50 for right now, but I'm going to go ahead and let the step be 1 week at a time. Okay. So here we go. Now it's counting by ones, 50, 51, 52. So it's something pretty close to 60 where they changed. Okay? Maybe somewhere in this area. So let me take a snapshot of this and see if we've got what we need. Okay, so here's some more data for Larry. 57, 58, 59 weeks. Alright, so that's some specific numbers between 50 and 60 there. Let's see if I got the right zone. Now let me go back and grab Gertrude. Now I've got Gertrude's equation back in the calculator. Okay. So I have it set to count by ones again. Alright, so here are the same three numbers for Gertrude. Let me cut and paste this. Alright, and here I have that same snapshot of Gertrude's weight over time. 57 weeks, 58 weeks, 59 weeks. Alright, so we can see, looking at 57 weeks, who weighed more at 57 weeks? Not by much, but at 57 weeks, Larry still weighed more. 140.4 compared with 139.4. Alright, Larry still weighed more. I probably shouldn't have circled this one. Okay, Larry weighed more, so I circled Larry. By the time we got to 59 weeks, who weighed more at 59 weeks? Now Gertrude weighs more, 137.8 compared with 136.8. Okay, so Gertrude weighed a pound more. So we went from Larry weighing more at 57 weeks to Gertrude weighing more at 59 weeks. So obviously by now you've probably seen it. If you look right at 58 weeks, who weighed more at 58 weeks? Trick question, right? Neither one of them weighed more at 58 weeks. At 58 weeks, they both weighed exactly 138.6 pounds. Okay, they both weighed 138.6. So that means 58 weeks, this is the point in time where they weighed the same. And that's actually what we were trying to find, isn't it? So ding ding ding, 58 weeks is the magic number. So looking back at the paper, we were supposed to tell after how many weeks will Gertrude and Larry's weight be the same. And it turned out that their weight will be the same after 58 weeks. Okay, after 58 weeks, Gertrude and Larry will both weigh, what did they weigh again? 138.6 pounds. Okay, and as far as the justification and showing mathematically, you could, if you had your two tables of values side by side, the way I do, of course yours would be written by hand, but this would be your mathematical justification. You could use your table of values to show where they match 58 weeks. Okay, so look, it's time to pause the tape, pause the video, because I want you to have a little bit of time to work on your own on Susie's age. If the substitute teacher or whoever's running this, go ahead and hit pause now, and then turn it back on in about 5 minutes or so, or whenever it seems like most kids have had a chance to work on Susie's age, this problem, this whole problem. Okay, I'm going to go ahead and get started. I'm going to assume that you pause the tape, and now everybody has worked, and now we're starting the tape again. So, what is going on with Susie's age? What are these variables? So I've got this equation. Okay. X is Susie's age in years. And then Y is Susie's height in inches. Okay, so I don't really like the name of this problem, because it's not really Susie's age that this is an equation of. This is really Susie's height. Alright, a better name for this would have been Susie's height, because that's the Y value, is Susie's height. Anyway, so this is an equation of Susie's height as a function of time. X is the years. Okay, so this is years, and this is height. Okay. This is a typo. This is an error. The question says, what does 3.4 tell us about the situation? There is no 3.4 in it. So that's wrong. So this should say 4.4. Okay, so the question is, what does the 4.4 tell us about the situation? Okay, what did you guys put for that? What did the 4.4 tell us about the situation? Alright, I don't know if you guys were just sitting there quiet and now I feel foolish or not, but hopefully somebody was saying something good. This whole equation is about height, and it makes sense that the height will be increasing over time. So this number in the front should be telling us how her height is changing for every year, because we're multiplying by years. So 4.4, we're talking height. What unit are we dealing with? We're dealing with inches. So this 4.4 means that Susie is growing 4.4 inches per year. X is years. So this is 4.4 inches every year. So you should have written that down. Hopefully you already have it, but I'm going to write it down now. Susie grows 4.4 inches each year. Okay, what does the 16 tell us about the situation? Okay, now let's be careful about this. Okay, X is supposed to be Susie's age in years. Okay, and overall this is giving us Susie's height in inches. So, what was Susie's age on the first day she was born? Okay, because if I want to know what this value on the end means, what I want to do is I want to imagine what would it mean for X to be 0, because that's the beginning of everything. So if X is Susie's age in years, if X were 0, that means that's the day that Susie's born. She is 0 years old. She is firstborn. She's not even 1 year old. So again, when you have a 0 term, that has the effect of 0 times anything is 0. So this entire term will go away. It will become 0. And that's just going to leave 16. Okay, so that means this 16 tells us Susie's height at age 0. In other words, this tells us that Susie was 16 inches long on the day she was born. So that's the answer to this question. What does the 16 tell us about the situation? Susie was 16 inches long when she was first born. Okay, because that means her age is 0. So notice, one more time, anytime we want to know what this number on the end is, imagine what it means for the variable to be 0. Because that will make this go away, and then that will tell you what this number on the end means. Anything else? Johnny is Susie's twin. So here's another equation for Johnny. Same deal. Alright, this gives Johnny's height y after x weeks. Well that's two different things. This is Susie's age in years, but this is Johnny's height in weeks. Okay, anyway, I'll have to be careful about the units and the comparison. That's a little bit odd that they're doing it that way. That might even be a mistake. I don't know. But there's one thing that we can be sure of. Who was taller when they were first born? Was Susie taller when she was first born? Or was Johnny taller when he was first born? Alright, well I'm hoping you can see here again, when Johnny was first born, that's when x, it would be 0. So if I cross out this term, this tells me how tall Johnny was when he was first born. So on the day he was born, Johnny was 19 inches. Okay, as opposed to on the day that Susie was born, she was 16 inches. So I can definitely say that Johnny was taller, or longer, I guess if he's lying down because he's a baby. But Johnny was taller when he was first born. So that's a good thing to compare. So let's write that down. Johnny was taller when he was first born. Okay. Now, I think that this weeks right here, where it says weeks, I think that's a mistake. Because people don't grow that fast. If this were really weeks, let me take away some of this extra red. If this were really weeks, this would mean that Johnny is growing 3.8 inches a week. That would be one fast growing kid. So, whoever made this sheet, I wasn't the one who made it, but whoever made this sheet made another mistake right here. This should also say years. Okay, now they match. Okay, so fix this on your paper. Okay, let me get rid of some of this extra red up here too. Alright, so that's another thing that we can now compare between the two. Who is growing faster? Is Susie growing faster? Hint, hint, hint. Or is Johnny growing faster? Alright, hopefully you can see that Susie is growing faster. Okay, because she's growing 4.4 inches every year, while Johnny is only growing 3.8 inches every year. Johnny started off taller with 19 inches versus 16, but Susie is growing faster. So at some point, they should be the same height, as Susie grows faster and eventually will become taller than Johnny. But another thing we can write as we compare is we can say that Susie grows faster than Johnny. Okay, so Johnny was taller when he was first born, but Susie grows faster than Johnny. Okay, I think I'll even put a but in there. One nice sentence. Now, at what age will Susie and Johnny be the same height? Show your work neatly and justify your answer mathematically. Alright, well last time I showed it by comparing tables of values. This time I want to do it a different way. Looking at these two equations, 4x plus 16 and 3x plus 19. Remember that y represents their heights. If we're trying to find out where their heights are the same, if the height is the same, that means these y values will be the same. Okay? In other words, if they're the same height, then these two expressions should be equal to each other. Okay? Let me show you what I mean. This whole thing is an expression for Susie's height, the 4.4x plus 16. And this whole thing down here is an expression for Johnny's height at any given time. Okay? So these two expressions I just circled, 4.4x plus 16 and 3.8x plus 19. These two expressions, if they are the same height, these two expressions should be equal to each other. So in other words, I should be able to make an equation. 4.4x plus 16, 4.4x plus 16. Alright, that's Susie's height, but Susie's height should equal Johnny's height, 3.8x plus 19. 3.8x plus 19. Please write this down. You're going to be handing these papers in, so please make sure to write this down. In fact, put your name on your paper right now before you forget. I can make these equations because we're saying that they will have the same height. If their height is the same, I should be able to set these expressions equal to each other because the expressions should equal both the same height, so they're equal to each other. Now remember, x represents the number of years that have gone by. In other words, x represents the age of both Johnny and Susie. They're twins, so they're both born on the same day. Okay, so this x, if we solve for it, it should be the x that causes their heights to be the same. So all we really have to do is solve for x. So that's what we're going to do. So anytime I see x's on both sides of the equation, what I want to do is subtract. Subtract the variable. Anytime you see a variable on both sides, take one of the variables and subtract it from both sides. I usually pick the smaller one and subtract that. Okay, so I subtract this, that way these will cancel out. Okay, so I need to do this. These are like terms. So 4.4 minus 3.8. Okay, that's 0.6. So what I have now is 0.6x plus 16 is equal to 19. Now I need to get x by itself, so let's subtract 16 from both sides like this. Okay, so that's going to give me 0.6x equals, alright, 19 minus 16, that's 3. So now I have 0.6x equals 3. Alright, I need to get x by itself. How do I get rid of this 0.6? Alright, hopefully you've learned that to get x by itself, I'm going to divide by 0.6 on both sides. Alright, that way the 0.6's cancel each other out. And that is going to give me x equals, okay, so I've got 3 divided by 0.6 here. Alright, 3 divided by 0.6. It's 5. So x equals 5. Okay, please remember what this represents. And I'm going to write this as a sort of little summary statement. We were being asked, at what age will Susie and Johnny be the same height? Please remember that x represents age. X is Susie's age. Okay, x is Johnny's age in years. So when we find this x being 5, okay, x years. So when we find this x is 5, this is 5 years. So Susie and Johnny are the same height after 5 years. Okay?
And that is how you do that. Okay, we're probably getting pretty close to the end of the period by now. If there's any more time left in the class period, then you should go ahead and turn over the paper and work on Tia's cable bill. Okay, so go ahead and turn over the paper and spend a little time working on Tia's cable bill. So go ahead and pause the tape. This is probably the end of the class period. If there's any extra time, then you can continue the tape and I'll record a little bit more. Okay, really quickly, let's take a look at Tia's cable bill and see if we can answer some of these questions real fast. Probably nobody is listening to this because you guys are already on your way to your next class. But anyway, Tia's cable bill. I have this equation. X represents the number of on-demand movies. Okay, so X has the movies. Okay, X movies that she watches. And T is the bill in dollars. Okay, this is the cost. Alright, how many dollars the cable bill costs overall. Okay, so what are they asking us? So, what does the 3.95 tell us about the situation? Let's see. Well, the 3.95, look what that's getting multiplied by. Okay, 3.95 for every X. What did X represent again? Movies. So, we're doing $3.95 for every movie, because that's what we're multiplying by. So, 3.95 per movie. That tells us that the 3.95 is the cost of each movie. Whoops, let me squeeze that in there. Cost of each movie is $3.95. What does the $52.95 tell us about the situation? Okay, again, this, if I want to know what this means, the number at the end, let X be 0. Now, so if I let X be 0, what does it mean for X to be 0? In this case, X is movies. So if X is 0, that means 0 movies, no movies. So this part of the bill goes away. The $3.95 per movie, there are no movies, 0 movies. But we still have to pay $52.95. That means the $52.95 must be the flat basic price of cable if you don't watch any movies at all. Okay? So this tells us that the basic cost of cable, if you watch no movies, is $52.95. Okay. Cabletown is offering a new plan. It looks like this. Let's compare and contrast. We'll use these two numbers to compare. Okay? Let's start with the number on the end. Let's start with the $63.95. Again, what does this number on the end tell you? This is still about movies. $2.95 per movie. What does the $63.95 on the end tell us? This is the basic cost you would pay if you didn't watch any movies. So for Cable Town, if you watch no movies, you pay $63, almost $64. For Tia's cable bill here, if you go with this plan, if you don't watch any movies, you're paying $52.95. So you're actually going to pay more with the new plan as far as the basic rate. Even if you watch no movies, you're going to pay more. So you should write that down as something to compare. The flat rate is more for the new plan. Okay, so if we're not watching any movies, we're going to pay more for the new plan. But let's look at that other part. What else is different? Okay, remember what this number tells us. $2.95 compared with, got to get rid of some of this garbage. $2.95 compared with $3.95. Okay? Do you remember what these things told us? $3.95, that's how much we're paying per on-demand movie for the original plan. But now we're paying $2.95 per movie. Okay? So we're paying less per movie. We're paying more for the basic rate, the flat rate, but we're paying less per movie. So I'm going to say, but you pay less per movie. With the new plan. Okay? So you start off paying more for the basic rate. But if you watch a lot of movies, you might end up paying less for the new plan if you watch a lot of on-demand movies, because you're paying less per movie. So it all depends. If you want to decide which plan was better for you, it would depend on how many movies you usually watch. So how many movies would make both plans cost the same amount? Okay, and again, I'm going to show this by solving an equation this time. I'm kind of done with looking at tables. That was a one-time deal. So let's solve equations from now on. Okay, so if I want the cost of the plans to be the same, that means I should be able to take these equations and set them equal to each other. So this equation, if the plans are supposed to cost the same, we're looking for where they cost the same, this equation should be equal to the other equation. So I'm going to start off with this one, 3.95x plus $52.95. Did I get that right? $52.95. Okay. And that should equal the other plan, $2.95 plus $63.95. X plus $63.95. Okay. If I solve this equation for x, please remember in both equations, x is the number of on-demand movies. X is on-demand movies. So if I solve this X, this will tell me how many on-demand movies it would take to make both plans cost the same. That's why I'm setting them equal to each other. So let's start solving this. What did I tell you to do anytime you have X's on both sides of the equation? What did I tell you to do? Hopefully somebody said it. Anytime you have X's on both sides of the equation, I want you to subtract. I usually pick the smaller x and subtract, but subtract that variable from both sides. So minus 2.95 from both sides. Alright, that way these will cancel each other out. Okay, I'm going to bring down my equal sign. Alright, 395 minus 295, well, that's a difference of $1. So this will be 1x, or simply just x. So I'm going to bring this down. So I've got x plus $52.95 equals $63.95. So of course, to get x by itself, I'm going to subtract $52.95 from both sides. So minus $52.95 minus $52.95. Okay, so that's going to give me x equals 11. Okay, so yeah, I've got x equals 11, but please do not forget what this means. Don't just put x equals 11 and move on to the next problem. You have to say what this means. This means 11 movies. Okay, so let's write that in the statement. If you watch 11 movies, 11 movies, the total cost will be the same. For both plans. Okay? Alright, that's where I'm going to have to end the video. Even if there's a little bit more time left in class, I'm going to leave working on the Algebux coffee problem for you to do on your own. Okay? Maybe this will be our warm-up in the next class to go over the Algebux problem. But if there's any more time left in class, spend the rest of class time working on the Algebux problem by yourself. That's the end, people. This is a long video.